makes VT less negative for P channel device and less positive for N channel with minus QD greater than QI. So actually this is referring to that equation, that VT equation, actually this equation. So if you increase CI minus QD by CI, you can here you can see actually if you take 1 by CI common in the expression of VT, let me write VT equal to twice phi A plus 1 by CI minus QD minus QI, তাই তো, প্লাস phi ms। তাহলে এখানে কি বলতেছে, for PMOS this is negative, for NMOS this is positive, for NMOS, for PMOS this is negative, right? So if you increase CI, what will happen from this equation? For PMOS, the negative quantity will reduce, right? So VT will become less negative for PMOS. Right? That's what is mentioned here. That increasing CI makes VT less negative for P channel device and less positive for N channel. So less positive for N channel, that means if this minus QD, this positive part is greater than the negative part, then increasing CI will make VT less positive for NMOS, right? So this is the effect of CI. So how can you increase CI? You can increase CI by decreasing D, that means thinner oxide layer, or increasing permittivity. Now, reducing D has some other effect. If you reduce the insulator thickness too much, then what will happen? There will be leakage through the insulator, right? If you apply a metal to semiconductor voltage, remember that is a capacitor structure. The insulator, the oxide is the dielectric. So in an ideal capacitor, what should happen? There should be no current through the dielectric. The capacitor plates, they should be insulated from each other by the dielectric. Now, if the dielectric layer, insulator layer, oxide layer is too thick, carriers can leak through the, pass through the dielectric. So there will be current through, okay. So you cannot reduce D too much. There is a limit. So what we can do, we can use a dielectric whose permittivity is higher, a dielectric other than silicon dioxide whose permittivity is higher than silicon dioxide. So if epsilon is higher, D can be made higher. Okay. Epsilon higher means what? CI will be higher. So in that case, you do not need a small d. You can use larger d to prevent the leakage through the gate oxide. Okay, so that kind of oxides are called high K dielectric. High K means permittivity. High K dielectrics have high permittivity. Okay, so high K dielectrics are sometimes used so that the thickness of the insulator can be kept reasonably high to prevent charge leakage through the dielectric. Okay. So for practical consideration, again back here, practical considerations, the high K gate oxide thickness is generally 10 to 100 angstrom, that means 1 to 10 nanometer in modern devices having sub-micron gate lengths. There are different types of high K dielectrics. Hafnium oxide I can think of one hafnium dioxide is a high K dielectric. There are also other high K dielectrics which are now being used instead of silicon dioxide. Okay, so control of CI. By controlling CI, you can control the magnitude of the threshold voltage for both NMOS and PMOS. So this is second way. First way was choice of gate electrode. Second was control of CI. And third is threshold adjustment by ion implantation. So this is actually very simple. The most valuable tool, simple and most valuable tool for controlling threshold voltage is ion implantation, since very precise quantities of impurities can be introduced by this method. It is possible to maintain close control of VT. So what is this? You remember threshold voltage is dependent on doping, right? The last class, last topic I have shown you. Here, threshold voltage for both PMOS and MOS, threshold voltage depends on doping level. Okay, so by controlling, this is the substrate doping. So by controlling the doping level of the substrate, you can control VT. Now, how can you control the doping level of the substrate? By ion implantation, you can fix a doping level at the substrate. And what is ion implantation? Ion implantation is actually a fabrication technique which is used to introduce different materials in the silicon. So in ion implantation, what happens is there is substrate. So this is the substrate. This is the wafer, the substrate. There are some ion guns. Okay. These guns, ion guns, shoot ion of particular material, particular element into the substrate. Okay. So say for example, this is P-type substrate. You want to modify the doping level of the P-type substrate. So you use a ion gun to shoot a acceptor ion, some kind of acceptor ion, say boron ion into the substrate. So what happens? These are highly energetic ions shoot by this ion gun. So these ions will penetrate the substrate, okay, and will go into the substrate. So once you implant or inject sufficient number of ions into the substrate, then you do a thermal annealing. You increase the temperature of the substrate to some point and then gradually cool it. So what will happen? Those ions will become part of the crystal lattice and actually will become an active dopant in the substrate. So that's how you can control the doping level of the substrate. And that technique is called again ion implantation. So ion implantation can be used to control the threshold level of the substrate, and by that you can control threshold voltage. Okay. So that is this threshold adjustment by ion implantation. The most valuable tool for controlling the threshold voltage is ion implantation, since very precise quantities of impurities can be introduced by this method. Okay, we can introduce precise amount of impurities in the substrate. So it is possible to maintain close control of VT, since VT depends on the doping level, as I mentioned. So these are the three uh, techniques for controlling threshold voltage before of course, this is before the fabrication. Okay, so this is a highly magnified version of a small, very small MOSFET. You can see metal is there. This is the gate. Here we have a high K dielectric. I don't know what dielectric they have used. Separate silicon high K gate dielectric. Gate transistor was made using gate law replacement intermediate process. This is actually a MOSFET made by Intel. Okay, picture of MOSFET made by Intel. This is TEM, transmission electron micrograph of silicon metal oxide semiconductor field effect transistor. Silicon germanium. These are source drain, and this is the substrate. Okay. This is, you can obviously understand, this is the metal connection to the source drain, and this is the gate. Okay, so these three techniques are useful to control threshold voltage during the fabrication. But once you have fabricated the threshold, sorry, but fabricated the MOSFET, that means you have already used a particular metal as the gate detector. You have already chosen a particular oxide and thickness for the insulator for the gate oxide, and you have already used a particular doping level of the substrate. So once you have made the MOSFET, actually the threshold voltage is fixed. Okay, by these three things: gate electrode, choice of gate electrode, CI, value of CI, and value of substrate doping. There is a technique to change the threshold voltage after the fabrication. That means after the fabrication, actually there is no way for you to change the gate electrode or the gate insulator or the substrate doping, but there is another way to control threshold voltage. We will come to that in the next topic, which is this substrate bias effect or the body effect. Okay, so these three techniques again are used during the fabrication of the MOSFET to control the threshold voltage of the MOSFET, which is being fabricated. But once the MOSFET is fabricated, then we can use this body bias effect or body effect to control the threshold voltage of the MOSFET. So what is body effect? Remember, in the previous discussions, all previous discussions, we have assumed that source and body are always shorted. Why source and body were shorted? Anyone remember why?
যাতে স্যার
So
অলওয়েজ
because
রিভার্স বায়াস
the
থাকে স্যার।
No, not always reverse bias. The source body junction never gets forward biased. That
জি স্যার,
was
ফরওয়ার্ড
the
বায়াস।
reason. This was body. Okay, this is oxide. This is gate. This is connection to source. This is source say. This is connection to
ওকে,
drain. This is gate. The source body is shorted always. That's what we have seen. So that this source to body PN junction, this PN junction, this
ফরওয়ার্ড
junction
বায়াস।
is never forward bias, never forward bias. But I told you that it is possible to make this junction reverse bias. That is allowed. Forward bias is not allowed, but reverse bias is allowed. So if you reverse bias this junction, then what will happen? That we will see. So we assume that the source S is connected to the substrate B. In fact, it is possible to apply a voltage between source and body with a reverse bias between the substrate and the source, VB negative for N-channel device. The source channel junction potential barrier is increased. Clearly, the gate must be biased more positively than the grounded substrate to lower the source channel potential barrier sufficiently to create an inversion layer. This causes the threshold voltage to increase with reverse bias substrate. This is known as body effect. I am explaining this in more detail. Let's see what are the text here now. Okay. So though it sounds difficult, but actually this is very simple logic. So let's draw this here again. If you draw, if you say this, we are talking about N channel device. So this is N, source is N, drain is N, body is P. So this is our body, B, source. This is oxide. This is gate. and this is drain. So in this is, remember, this is N channel or NMOS, right? So how can you make source body junction reverse biased? You tell me what should be the polarity? Hmm?
স্যার বডির সাথে নেগেটিভ দেবো স্যার।
Hmm. Body negative, source positive, right?
জি স্যার।
So obviously for PMOS this will be opposite. For PMOS, source is P type, drain is P type, body is N type. So this polarity will be opposite, right? For PMOS. Naki. Here
ইয়েস স্যার।
VSB is positive. For PMOS, VSB has to be negative.
নেগেটিভ।
Simple. Nagi. Understood?
জি স্যার বুঝছি।
Okay.
Yes,
Now
sir. Yes.
when source and body were shorted,
সোর্স পজিটিভ কেন ধরবো স্যার একটু বুঝাবেন?
sorry,
স্যার যে লাস্ট কোশ্চেনটা স্যার, সোর্স পজিটিভ ধরবো স্যার, এই পার্টটা একটু আরেকটু ক্লিয়ার করলে ভালো হতো স্যার।
এটা NP PN junction. You want to reverse bias the PN junction. This P, this N, this PN junction. You want to reverse bias. So what polarity should you connect to N and what polarity should connect to P? You tell me to reverse bias the PN junction.
স্যার পি তে নেগেটিভ।
P negative. So that is the thing. Negative, positive. So here V is B positive, right? Or you can say V B is negative. Same thing. Understood?
জি স্যার।
So when source and body were shorted, remember we had a depletion layer like this, right? Remember drain source is already, there is a VDS is positive for NMOS, right? So VDS positive means drain is connected to positive voltage. So drain to body, this junction is reverse bias. So this depletion layer, drain to body depletion layer is wider. Okay. But when source body was shorted, we had just a depletion layer corresponding to the equilibrium depletion layer, right? V naught. The voltage across the depletion layer of source body PN junction is V naught, contact potential. Now, when you reverse bias this source body junction, what will happen to the depletion layer? Source body depletion layer. You tell me.
Will increase.
Hmm? Definitely. This
Will increase.
depletion layer will widen, right? This depletion layer will become more wide, right?
ইয়েস স্যার।
So this depletion layer becomes more wide means where? Below the gate, you can see we have something like this, right? Now we have something like this. So below the gate, the depletion layer is increasing, right? Just below the gate, depletion layer has increased. So in terms of charge, what does that mean? Below the gate, the depletion layer charge has increased, right?
ইয়েস স্যার।
So what do we have in the depletion layer? In this case, we have negatively ionized acceptor atoms, right? Hmm? So here, because of this reverse bias, the depletion layer charge QD has increased. Remember, there was a term minus QD by CI. So increasing QD means what? you want to have a certain concentration of electron in the inversion channel, in the channel, inverted channel, right? So in order to get same concentration of inverted, same concentration of electron in the channel, total negative charge here has increased, has to increase before the reverse bias case, right? When source body was shorted, the total negative charge here and reverse bias source body, total negative charge here. In this reverse bias case, total negative charge here has to be larger,
larger.
more. So this is, remember, AMOS, this is a capacitor structure. So total negative charge must be equal to total positive charge. So in this case, the total positive charge on the gate has also need to
Should be
increase, right? So
Yes, sir.
in terms of gate voltage, what does that mean? You need more positive gate voltage to create the
Yes.
same level of inversion, right?
Yes, sir.
So in terms of VT, what does that mean? The threshold voltage magnitude has to increase,
Hmm.
right?
Yes, sir.
So by applying this reverse bias, you can increase the magnitude of threshold voltage. Understood? So this is the body effect. You are applying a bias in the body. In this case, you are applying a negative voltage to the body. And by applying a negative voltage to the body, you are increasing the magnitude of the threshold voltage for this transistor. So this is the body effect. Okay, so this is actually mentioned here, but in a language which may not be understandable to you. Okay, so uh, let's read it again. In fact, it is possible to apply a voltage between source and body with a reverse bias between the substrate and the source, VB negative for N channel. So you can understand this is N channel. So the body bias is, has to be connected to a negative voltage. VB negative for N channel device. The source channel junction potential barrier. Source, they are talking about actually this channel, but actually there is a junction here, source to body. Source channel junction potential barrier is increased. Clearly, gate must be biased more positively than for the grounded substrate. Grounded substrate means the previous case when source and body were shorted and actually source were grounded. To lower the source channel potential barrier sufficiently to create an inversion layer, this causes the threshold voltage to increase, and with reverse substrate bias, this is known as the body effect. Okay. So now you understand probably, right? Reverse biasing causes the depletion layer charge to increase because source to body depletion layer is widening. So the depletion layer below the gate is widening, the depletion layer charge is increasing. So to achieve the same layer of inversion charge or inversion layer charge, we have to use more positive charge on the gate. That means more positive voltage on the gate. So threshold voltage is increased. So this is the body effect. So if I tell you now, explain the body effect of a P channel device, can you do that? Will you be able to do that? For P channel, what will happen? The substrate is what type of substrate is there?
N
N
type.
P
type.
সেলেনে বডিটা এন
So,
টাইপ থাকবে স্যার।
uh, and drain gate are PP, right? So this
জি
is the
স্যার।
oxide. This is the gate. So this is the drain connection. This is the gate connection. This is the source connection. This is the body connection. So we have to remember for P channel, VSG has to be positive. That means VGS negative, and VSD has to be
Don't-
positive. That means VDS has to be negative. Now, previously source body was shorted. Now the junction has to be reverse bias. So to reverse bias this PN junction, we have to connect source to negative with respect to body. So we have to apply a positive bias to the body, right?
Yes, sir.
So when you do that, same thing happen. This depletion layer,
Will
source to
increase.
body depletion layer will widen. So the below the gate, we have now more depletion layer charge. So more depletion layer charge means what? Positively ionized donors
Donor.
here, right?
Yes, sir.
So total positive charge yeah, below the gate will increase. So in order to
So
balance that, we need more negative charge on the gate. That means we need more negative voltage,
VG. Yes.
VGS. So threshold voltage magnitude will increase. That means threshold voltage will become more negative. Or technically speaking, we can say threshold voltage will reduce, right? If previously it was minus 2 volt, now it will be say minus 3 volt or minus 3.5 volt. Threshold voltage magnitude will increase, or you can say threshold voltage will become more negative. So for N channel, the body bias will cause threshold voltage to become more positive. For P channel, the body bias will cause threshold voltage to become more negative. That means in both cases, threshold voltage magnitude will increase because of body bias. Understood?
Yes, sir.
And the polarity, what polarity should we need? Source to body, that should also be understood, right? For P channel, for N channel. Naki, this is
So can
actually, hmm?
sir, can you
Yes,
decrease threshold voltage in similar way?
no, only increasing is possible. Magnitude increase is possible. Because
Okay,
as
sir.
I mentioned, the source to body PN junction, this can all only be reverse biased or shorted. Shorting means source to body voltage is zero. Applied external voltage is zero. But you cannot apply a positive source to body voltage. You cannot forward bias the source body PN junction. Okay. So only in reverse bias is possible, and so only increasing threshold voltage is possible. Okay. So the net result is that the depletion region in the channel is widened. So here they are saying the thing I have said. Depletion layer in the channel is widened, and the threshold gate voltage required to achieve the inversion must be increased to accommodate the larger QD. So since depletion layer charge is increasing, so that's why your gate voltage has to increase. Okay. So the amount of increase of threshold voltage due to body bias is this. It can be shown del Vt. Del Vt is the increase of the threshold voltage root over twice epsilon S. Epsilon S is the silicon permittivity QNA by Ci minus Vb to the power half. Why minus Vb? For N channel, Vb itself is negative. Okay. As I mentioned, body is connected to negative voltage. So body voltage, Vb itself is negative, you can say. VBS, a source is being used as the reference node. Okay. VGS, VDS, VBS. Okay. So source is the reference node. So VGS positive, VDS positive, VBS negative. So that VBS is actually this V. Yeah. So VBS negative and that negative. Negative, negative minus VBS will become positive. So that to the power half. So the increase of threshold voltage is proportional to square root of the reverse bias voltage. Okay. So total threshold voltage is that threshold voltage Vt with VBS 0 plus del Vt. Okay, this del Vt. Now Vt with Vbs equal to 0 means what? This is equal to that previous equation, twice phi f minus Qd by Ci minus Qi by Ci plus 5ns. So this is the equation with Vbs equal to 0. As I mentioned previously, we have assumed source body shorted. Source body shorted means Vbs is equal to 0. So Vt with Vbs equal to 0, which is the equation we have derived earlier, plus the increase of threshold voltage due to body bias. This. So this will be the total expression of the threshold voltage. Understood?
Yes, sir.
Hmm. And in case of this is for N channel, so for P channel, what will happen? I believe you can deduce from there, right? Del Vt. Hmm. For P channel. So, like I said, for a P channel device, oh, I haven't read this yet. So where Vb will be negative for N channel case, as the substrate bias is increased, the threshold voltage becomes more positive. You can understand this. This del Vt is positive. Now, for P channel device, the bulk to source voltage Vb is positive to achieve the reverse bias, and the approximate change Vt is given by this. So for P channel, if you remember, Vbs is positive, right? For P channel, VGS is negative, VDS is negative, VBS can be positive, reverse bias. So since VBS is positive, source is the reference node. So VB is positive. So VB to the power half, you can see. So del Vt. So for P channel, again Vt equal to Vt with VBS equal to 0. That means the previous expression plus del Vt. Here this del Vt is negative if we have seen. Notice this del Vt is negative. So this is already negative and this is also negative. So total Vt will be more negative because of body bias. Okay. In the P N channel case, say this Vt is positive. This is plus, right? For P channel, there is a negative sign. So this threshold voltage will become more negative. So thus for P channel, threshold voltage becomes more negative with substrate bias. Understood?
Yes, sir.
So hooray, we have finished chapter 6. Threshold voltage MOSFET, we are done. Okay. So
Alhamdulillah.
this week, by next week, beginning of next week, I believe we will be able to finish BJT, and the end of the next week, I will take the third quiz on FETs, MOSFET and BJT, and the CO3, course out objective 3, course outcome 3, FETs, sorry, transistors, FET and BJT, transistors. So that will be, আসসালামু আলাইকুম ভাবি, হ্যাঁ ভালো আছেন। CO3 is about transistors, so field effect transistors and bipolar junction transistor. That will be the combined syllabus for quiz 3 to be held next week, probably Friday or Thursday. Depend. You give me the date. Hopefully, I will be able to finish BJT by next Monday. Not this week, Monday of the next week, not tomorrow. Tomorrow, then Thursday, then Monday. By that, I will be able to finish BJT. Okay, actually, today I will start BJT. MOSFET is done. So let's move on to new chapter, chapter 7, bipolar junction transistor. So if you remember, MOSFET is a unipolar device. N channel only electrons flow, P channel only holes flow, but BJT is a bipolar device, both electrons and holes flow. But obviously, you will see later that mostly one type of though both will flow, but one type of carrier will be dominant. Okay. So bipolar means you can understand two polarities. So both hole and electrons are the carriers. You have, I believe, fundamental idea about BJT, but I will review some things. So in this chapter, we shall use a PNP transistor for most illustrations. Why? Because the main advantage of PNP for discussing transistor action is that whole flow and current in the same direction. In PNP transistor, the dominant carriers are holes, and whole flow direction and current flow direction is same. So it's easier for us to understand actually the working of the transistor. But once we understand how PNP works, it will be able, we'll be able to actually explain how NPN works also. Similar to MOSFET. In MOSFET, actually, for all illustration, we have used NMOS. But once we have understood NMOS, it is possible for us to explain operation of PMOS also. Same thing here. Here we will use PNP to explain things, but once we have understood that, NPN can be understood. Okay. So this makes the various mechanisms of charge transport somewhat easier to visualize in a preliminary explanation. Once these basic ideas are established for the PNP device, it is simple to relate them to more widely used transistors, NPN. So fundamentals of BJT operation. Let me, I will read it later. Let me first explain things. I will discuss up to this today. So you remember reverse bias PN junction, right? PN, reverse bias. So reverse bias PN junction has a wide depletion layer, right? Right? Plus, 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 positively have positively ionized donor. We have negatively ionized acceptors, right? Now, what is the current through the reverse bias PN junction? Mm-hmm. The current through the reverse bias PN junction is what? Hmm?
Sir, ideally it is zero, but a very few amount of current passes through it.
That current is the reverse
The
saturation current.
minority.
And
Reverse saturation current.
what is the source of this current?
So
The
the
minority
Carrier.
carrier.
in the neutral region, sir.
Mm-hmm.
But sir,
The
electrons and
minority
holes in the
carrier.
neutral region.
The thermally generated electrons and holes within the depletion layer and also within the neutral region close to the transition region edge within one few diffusion length, right? From the transition region edge. So the carriers which are generated in the neutral region close to the edge, what happens to those carriers? Those carriers have a chance to diffuse into the depletion layer, right? When a carrier is generated in the neutral region, an electron hole pair is generated locally, the concentration has increased. So there is a possibility of diffusion. So if this generation point is close to the transition region edge within one diffusion length, there is a possibility that these carriers will diffuse here. Once they diffuse here, the electric field in the depletion region will drive electrons to go to this side and holes to go to this side. So this transport of charges will create a current, and that is this reverse saturation current. And this current depends on what?
Sir, the
I
amount of
explained.
voltage applied.
No. I explained this actually in PN junction. This depends on the rate of EHP generation near this transition region edge. That means thermal generation of carriers. Once these carriers are generated, if they diffuse here, they will sweep. How fast the carriers will move within the depletion layer, that does not determine the current, because here the bottleneck is how many carriers are available for this current, for creation of this current. And that bottleneck is the thermal generation of carriers here and here within one diffusion length from the transition region edge. Okay. So once they are available, they will quickly sweep through the depletion layer once diffused. So here bottleneck is how many carriers, EHPs, are being generated thermally per unit time, say per second. And that is solely determined by the temperature. If you increase the temperature, reverse saturation current will increase. If you decrease the temperature, reverse saturation current will decrease. So electric field within the depletion layer, or the voltage reverse bias across the depletion layer, reverse bias voltage, they have nothing to play, no role to play in determining the magnitude of the reverse saturation current. These things I'm pretty sure I explained in the PN junction. Okay, but probably you have forgotten. So this will give you a review. So again, reverse saturation current depends on temperature, because actually it depends on the thermal generation rate of carriers, EHPs, which depends on the temperature. Understood? Any question here?
No, sir.
The electric field within the depletion layer, that means the voltage across the reverse bias voltage, do not play any role to determine this magnitude, because the bottleneck, again, the bottleneck here is how many carriers are being generated per second within one diffusion length from the transition region. That is the bottleneck. Whenever a carrier is available, that can sweep. Okay. So if you have understood this, now say a situation where we have a PN junction, reverse bias PN junction, minus, 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 plus, plus, plus. Instead of, in addition to thermal generation, say we are supplying optical energy also. So there can be optical excitation of carriers also. So what will happen? We are supplying photons, reverse bias PN junction. This is also reverse bias PN junction, minus, plus. So these photons, of course, here H nu is greater than Eg. Photon energy is greater than the band gap energy. So this optical energy, photon energy, will create more EHPs, right?
Yes, sir.
So close to this depletion layer edge, more EHPs will be created. So what that will do to the reverse saturation current?
It will increase, sir. Reverse saturation
Increase.
current.
Reverse saturation current will increase. So this increase of reverse saturation current will depend on what?
Sir, optical excitation, thermal.
Thermal plus optical. Thermal say temperature is constant.
তাহলে স্যার optical
So it
excitation
will depend on how many photons we are
The optical
supplying per
generation rate.
second. Right? Yes, exactly. Optical generation rate. So if we supply more photons per second, the reverse saturation current will increase more, right?
Yes,
Reverse saturation current will depend on optical excitation rate, right? So if the dark current means when there is no optical excitation, only thermal generation is going on. During that time, the current that we can say that is the dark current without any optical excitation. So if the dark current is very small compared to the optically generated current, then we can say the current here in the through the reverse bias PN junction is actually proportional to the optical excitation rate, right?
Yes, sir.
Can you say that? Okay. So
Yes, sir.
here again, the voltage or the electric field across this this depletion layer is immaterial. It doesn't matter. The magnitude does not determine the amount of current, reverse current through this PN junction, right? Only the optical generation rate or the number of photons being supplied per second, that determines the current, right? Understood? Since we have seen that reverse bias voltage or the electric field in the depletion layer, they do not play any role in determining the amount of current here, reverse current here. Only the number of available carriers here and here, that determines the current. So since the number of carriers available here and here depends on the optical energy, optical excitation rate. So this optical excitation rate determines the current. Up to this, okay?
Assalamualaikum, sir.
Yes, walaikum salam.
Does it mean the electric field wouldn't like increase the number of EHPs generated?
Sorry, it's peak field.
So I mean, does it mean if you have like a strong electric field here in this junction, would it not increase the number of EHPs generated?
No. ESP generation has nothing to do with the electric field. ESP generation depends on the amount of energy we are supplying externally, thermally or optically. Okay. Which I mentioned actually here. I already explained that here.
So
Same thing
because
will
when
happen here. Sorry?
because you said in the explanation of when you introduce this PN junction, you talk about
Uh,
an electron being accelerated and then on possible collision with the lattice atom, it could knock out electrons in the atoms.
Sorry, I do not understand.
Because when you introduce the PN junction, you talk about the strength of the electric field could accelerate the electrons or the charge carriers.
Accelerate the electron, but if you have only 1 electron per second, say for example, 10 electrons per second you are getting. So what will be the current through this? At per second, maximum 10 electrons can pass through this. Because you can get at most 10 electrons per second. So who is determining the current now?
Okay, the amount of electrons supplied
The
from the other.
number of electrons supplied. Okay. We have high electric field here, but only having electric field there is not sufficient. You have to supply carriers here. So you are supplying 10 carriers, 10 electrons per second here. So the current will be 10 electrons per second. As simple as that. Understood? It doesn't
Yeah, I
matter
get this.
how strong the field here is.
Okay.
So same thing here. Here the carriers are coming from thermal generation and optical generation. So that number of carrier is determining the current. Okay, the field within the depletion layer uh, does not matter actually. So if you have understood this, now come a hypothetical scenario where we have a whole injection device. We have a reverse bias PN junction. PN, which is reverse biased. Plus, 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 minus, minus, minus. Here, within one diffusion length, say this is one diffusion length. Within one diffusion length, we have a whole injection device. This is a whole injection device. We inject holes here. this is less than LP. This W is less than LP. So if you this whole injection device is injecting holes in this region. So since this width is less than 1 diffusion length, these holes have a possibility to diffuse within the depletion layer. So what will happen? Those holes will be swept to the P side, right? Giving rise to a current, right? And this current will depend on what? Again, this current will not depend on the electric field within the depletion layer. This current will depend on the hole injection rate. How many holes are we supplying? This whole injection device supplying here per second. That will determine this current, right? Am I clear?
Yes, sir.
So now how can we provide this whole injection device? Any idea? This part you should be able to figure out. What can be used as a whole injection device?
So People's injunction.
This, remember, this PN junction is reverse biased. Now, if you use a P plus N junction, which is forward biased. So in a P plus N junction, the current constitutes of mostly what? What type of carriers?
Holes.
Holes.
Holes. Why holes? Remember, I not. There was a question in mid, right? dP by LP PN plus dN by ln NP. Rings any bell? So for a P plus N junction, this guy is much less than this guy, right? So this we can eliminate, naki? We can neglect. So the current mostly constitutes of hole going from P to N. Very small amount of electron will go from N to P, this NP. Remember that? So this forward bias N plus P junction will act as a hole injection device. So this forward bias P junction will inject hole here, but of course there is a depletion layer here, thin depletion layer. So this is the neutral N region. The width of the neutral N region must be less than the whole diffusion length. So if you remember, in a forward bias PN junction, what happens? PN, this is depletion layer. So here we inject holes, right? Minority carriers. Remember, there was actually equation derivation also in the exam. This is the amount of injected holes in this at this plane, right? X and naught. From there, we can get del P xn equal to del Pn e to the power minus xn by Lp. Remember?
Yes, sir.
So here we are injecting this much, and from there diffusing, recombining, right? So here we have whole current which will gradually convert to electron current, right? From hole diffusion to electron drift current. Remember that? So the total current is constant. So here the same thing will happen. We are injecting holes in this plane by applying a fixed bias here. So minority carrier injection, we are injecting holes here. If this neutral region width is less than the hole diffusion length, then those holes have a possibility to diffuse into this depletion layer of the reverse bias PN junction. And once they diffuse, they will go to this. So this current depends on the hole injection rate here, which in fact depends on this forward bias voltage, right? This QV, this voltage, right? So in a sense, this is a controllable constant current source. The current through this PN junction depends on this voltage, this external bias, right? Controllable constant current source. This current depends on this V, this e to the power QV by KT. This determines the amount of hole injected, and the amount of hole injected determines, or hole injection rate determines this current, this reverse current. So eventually this current IC, this is actually, we will see later, this is IC collector current. This depends on this voltage. Okay, so this is the principle, basic principle of BJT operation, PNP transistor, of course. Understood?
Yes.
Okay, so let me read fundamentals of BJT operation. You see, this is, they have initially used the optical generation, that example. Then this is the hole injector. We are injecting holes here. So what will happen to the reverse bias PN junction? Let us begin the discussion of bipolar transistors by considering the reverse bias PN junction diode of figure 7.1. The reverse saturation current through this diode depends on the rate at which minority carriers are generated in the neighborhood of the junction. Neighborhood of the junction means close to the depletion layer edge, Xn naught, Xp naught. The reverse current due to holes being swept from N to P is essentially independent of the size of the junction electric field, and hence is independent of the reverse bias. The reason the hole current depends on how often minority holes are generated by EHP creation within a diffusion length of the junction, not upon how fast a particular hole is swept across the depletion layer by the field. These things I have already mentioned. How fast the hole is passing through the depletion layer, that is immaterial here. The bottleneck is how many holes are available for passing through. Okay, so that's what determines the current. So as a result, it is possible to increase the reverse current through the diode by increasing the rate of EHP generation. Okay, so by increasing temperature, you can increase EHP generation, and by that you can increase the reverse saturation current. One convenient method for accomplishing this is optical excitation of EHPs with light, which H nu greater than EZ, which I already mentioned. With a steady photoexcitation, the reverse current will still be essentially independent of the bias voltage, that means the reverse bias voltage. And if the dark saturation current is negligible, dark current, that means current without any optical excitation, current due to only thermal generation, that is the dark saturation current, is negligible, the reverse current is directly proportional to the optical generation rate, GOP. Actually, in photodetector, you will learn about photodetector in chapter 8. photodetector works on this exactly this principle. Okay, to determine the level of illumination, how many photons are there per second, to determine that photodetectors are used. And photodetectors use reverse bias PN junction. Okay, so the current through the reverse bias PN junction actually indicates the amount of light falling on the what should I say, the junction, reverse bias PN junction. Okay, so that's how photodetectors work. Okay, so the example of external control of current through a junction by optical generation raises an interesting question. Is it possible to inject minority carriers into the neighborhood of the junction electrically instead of optically? If so, we could control the junction reverse current simply by varying the rate of minority carrier injection. For example, let us consider a hypothetical hole injection device as in figure 7.1c, that means this figure, hypothetical hole injection device. If we can inject holes at a predetermined rate into the inside of the junction, the effect on the junction current will resemble the effects of optical generation. The current from N to P will depend on the hole injection rate. Okay, and will be essentially independent of the bias voltage, that means the reverse bias voltage. There are several obvious advantages to such an external control of a current. For example, the current through the reverse bias junction would vary very little if the load register RL were changed. Okay, so this RL. This will not actually determine the current through this PN junction. Okay, the current through this PN junction is determined by how many poles we are supplying per second, not on this load. So this is again very important aspect of this control, that current is determined by this. So if we keep this constant, current is constant. So this is a controllable constant current source. Constant current because this determines the current, and controllable because we can control this whole injection rate to control the current. Okay, so very little if the load resistance RL were changed. Since the magnitude of the junction voltage is relatively unimportant, therefore such an arrangement should be a good approximation to a controllable constant current source. A convenient hole injection device is a forward biased P plus N junction. The current in such a junction is due primarily to holes injected from P to N region, sorry, P plus region into the N material. If we make the N side of the forward bias PN junction the same as the N side of the reverse biased junction. So this is the figure actually you can see. This junction is forward bias, this is the reverse bias. So a PN junction, this PN junction is reverse bias. The same N side serves as the side of a forward bias P plus N junction. Okay. So the N is common. So forward bias junction is the same as the N side of the reverse bias junction. The P plus NP structure of figure 7.2 results. With this configuration, injection of holes from the P plus N junction into the center N region supplies the minority carrier holes to participate in the reverse current through the NP junction. So as I mentioned, you are supplying holes in this N region, and this N region width, this WB has to be much less than LP. So these holes will diffuse in this depletion layer of the reverse bias PN junction, and will be driven to the P side. So of course, the red part, of course, it is important that the injected holes do not recombine in the N region, that means the middle N region, before they can diffuse to the depletion layer of the reverse bias PN junction. Thus, we must make the N region narrow compared to the hole diffusion length. Remember, diffusion length gives you a measure how far a hole can diffuse before recombining. So if the width is less than diffusion length, then a hole can cross that distance without recombining. Okay. The holes must not recombine here. The holes injected here must diffuse here. Okay, in this reverse bias depletion layer, so that they can go to the other side. So that's why it is important that the width of the neutral N region, which is WB, this has to be less than the hole diffusion length. So up to this, understood, everyone?
Yes,
Hmm?
sir.
Okay. So here, the structure we have described is PNP BJT, the forward bias junction that injects hole into the center N region is called the emitter junction. I believe you probably know this, right? So this is the emitter, this is the collector, and the middle layer is the called base. Emitter, collector, base. And the reverse bias junction that collects the injected holes is called the collector junction. So we have emitter based junction here, and we have collector based junction here, EBCB. The P plus region, which serves as the source of the injected holes, is called emitter, and the P region into which the holes are swept by the reverse bias junction is called the collector. Emitter, this is collector, emitter, and middle layer is base. The center end region is called base. The biasing arrangement in figure 7.2 is called common base configuration, since the base electrode B is common to emitter and collector circuit. So you can see the voltages applied here. Base is the common point, reference point. We have applied an emitter base positive voltage and collector base negative voltage. So base is common. Emitter base, collector base. So this is a common base configuration. Probably you have seen there is common emitter collection configuration, there is common collector configuration. This configuration is common base configuration. So to have a good PNP transistor, we would prefer that almost all the holes injected by the emitter into the base be collected. Collected means all the holes injected by the emitter should diffuse to this reverse bias junction so that they can go to the P side. So all the holes coming from P plus should be able to go to the P, from emitter to collector. Okay, for a good transistor, for a good BJT. So thus the N-type base region should be narrow and the whole lifetime tau P should be long there. Okay, because as I mentioned, holes must not recombine here in the base region. So whole lifetime in the base region should be long. This requirement is summed up by specifying WB is much less than LP. WB again is the width of the neutral N region. Okay. At one side of the N region, we have a forward bias depletion layer edge, and the other side we have reverse bias depletion layer edge. So in between we have a neutral N region, WB. This WB has to be much less than the full diffusion length. Where WB is the length of the neutral N material of the base measured between the depletion regions of the emitter and collector junctions. And LP is the diffusion length for holes in the base, which is equal to root over dp tau p. With this requirement satisfied, an average hole injected at the emitter junction will diffuse to the depletion layer of the collector base junction without recombination in the base. A second requirement is that, so this is the first requirement, that WB is much less than LP. Now, second requirement is that the current IE crossing the emitter junction should be composed almost entirely of holes injected into the base rather than electrons crossing from base to emitter. As I mentioned, there is PN, there is NP, right? If through a forward bias PN junction, actually here holes will be injected to N side and electrons will be injected from N to P side. But this part, we can make it is small, electrons injected from N to P side. We can make this small by using heavier doping on the P side, right? As I mentioned, NP is much less than PN. This can be done by using P plus N junction. So that is the second requirement. This requirement is satisfied by doping the base region lightly compared to the emitter so that the P plus N emitter junction of figure 7.2 resolves. So it is clear that the current IE flows into the emitter of a properly biased PN junction, PNP transistor, and that IC flows out of the collector, since the direction of the whole flow is the same from emitter to collector. However, the base current IB requires a bit more thought. In a good transistor, the base current will be very small since IE is essentially whole current and the collected whole current IC is almost equal to IE. So here you can see actually a picture. In the emitter, you are injecting your holes are going, and these holes are being injected into the base region, which are collected to the collected in the collector region, right? Now, what will happen in the base? Actually, some things will happen. One thing is, since this emitter by base junction is forward biased, in addition to hole being injected from P to N, there will be some, though small, but some electrons being injected from N to P. That is a part of the forward bias current, right? As I mentioned, dP by LP PN plus dN by ln NP, NP. So this part, this is the electron injected from N side to P side. Though it will be much smaller than this, but still there will be some electrons there. And also there will be some recombination of holes in the base. Okay, though the width is small, less than the diffusion length of a hole, but still in the base region, some recombination will happen. So we have to supply the lost electrons because holes will recombine with whom? With electrons. So the electrons, some electrons from the N region is being lost. So we have to resupply those electrons. So some electrons must go from N to P side forward bias. Some electrons must be used to, what should I say? To replenish the electrons lost in the recombination. And also, remember, not only holes will go through this reverse bias PN junction, there will be some thermally generated electrons which will go from this P to N side. Reverse saturation current, thermally generated. So in the base region, actually we have 3 electron currents. One current going from N to P, forward bias N to P junction. One current going from this collector to base, reverse saturation current from thermally generated carrier, and one part of the electrode current comes from the battery to replenish the electrons lost in the recombination. Okay, so in the base region, there are actually 3 electron currents, but of course, the combined 3 electron currents is much smaller than the total hole current, because of the way we have designed the transistor. So that is what actually meant here. There must be some base current, however, due to requirements of the electron flow into the n-type base region, we can account for IB physically by 3 dominant mechanisms. The 3 mechanisms I just mentioned. There must be some recombination of injected holes with electrons in the base, even with WB much less than LP. The electrons lost to the recombination must be resupplied to the base contact. So remember, we have this negative terminal connected to the base. So the electrons lost in the base in the recombination, those electrons can be resupplied by the battery. So electron will flow in this direction. That means base current will flow in which direction? Opposite direction, right? IB. So this is one part of base current. Then some electrons will be injected from N to P in the forward bias emitter junction, even if the emitter is heavily doped compared with the base. These electrons must also be supplied by IB. So this base current should have also another component which I mentioned, that base to emitter electron injection, minority carrier injection. That component is also there, though it is a small, but that component is also there. So this will be another component of the base current IB. And the third component of IB is some electrons are swept into the base at the reverse biased collector junction due to thermal generation in the collector. So electrons generated here in the collector, they can diffuse to the depletion layer of the reverse bias collector base junction and be swept to the base region, which will actually reduce the base current. These two components, the replenishing of lost electrons and minority carrier injection from base to emitter, these were additive and will increase base current, but this reverse saturation component of electron current will actually reduce the base current because they are supplying the electrons to the base. Okay, some electrons are surface. This small current reduces IB by supplying electrons to the base. So base current consists of these 3 elements, 3 components. The dominant sources of the base currents are recombination in the base and injection into the emitter region. Okay, so the first two, these two are the dominant. Both of these effects can be greatly reduced by device design, as we shall see. In a well-designed transistor, IB will be very small fraction, perhaps 1/100th of IE. So IE is almost equal to IC. Though KCL, Kirchhoff's current law, says that as per Kirchhoff's current law, what from this is IE, IC, IB. IE should be equal to what? IC plus IB. Since IB is very small, so we can say IE almost equal to IC. So in a NPN transistor, the 3 current directions are reversed since electrons flow from the emitter to collector. Holes must be supplied to the base. The physical mechanism of operation of NPN can be understood simply reversing the roles of electrons and holes of the PNP transistor. So PNP, everything happens is explained in terms of pole because it is easier for you to understand the whole flow direction, current flow direction same. In case of NPN, you have to consider electron flow. So electron flow, you know that electron flow direction, current flow direction are reversed. So accordingly, you have to adjust the things. I believe if you think about it, you can actually figure out how the NPN works if you have understood the PNP. So today up to this, any question? বোঝা গেছে?
স্যার স্যার কুইজ রিলেটেড একটা প্রশ্ন ছিল।
হুম হুম
বলতেছি স্যার সিলেবাসটা স্যার মোটামুটি স্যার বড় হয়ে যাচ্ছে স্যার, শুধু ফেড সিলেবাসটা হলে ভালো হতো, কুইজে শুধু যদি চ্যাপ্টার 6 হতো স্যার।
এই কিন্তু যে CO3 হচ্ছে না, যে CO3 দেওয়া না ইয়াতে, ট্রানজিস্টার ইজ আউট, CO3 আই বিলিভ, নাকি কোর্স আউটকাম 3?
স্যার ফোর্থ কুইজে ওইটা নিয়েন স্যার, ঈদ টিদ গেল স্যার, পড়ালেখা একটু স্যার একটা বড় সিলেবাস স্যার, আরো সমস্যা হয়।
এই জন্য তো আগে থেকে বলতেছি, কুইজ উইল বি next week, not next week, next week, right? So which day do you prefer for quiz? Friday, Wednesday, Thursday? আগের কুইজ গুলো কোন দিন নিছি আমরা মোস্টলি, খেয়াল আছে? ভুলে গেছি আমি।
Friday.
স্যার শুক্রবার নিয়েছিলেন।
শুক্রবার। So today is 13, 19th is next immediate Friday, then 26th I am planning to take the quiz on 26th. So we have a lot of time to prepare for
জি
the
স্যার, তাইলে
quiz.
ওকে স্যার।
I am not talking about 19th. I am talking about 26th. Probably
ওকে স্যার, ওকে।
this Monday and Thursday. Within these two classes, I will be able to finish BJT. Okay. So
জি স্যার।
Friday after that, not the in that week, Friday in the following week, I will be taking the quiz. So we will have a lot of time to prepare.
ওকে স্যার, ওকে, দেন নো প্রবলেম।
Okay, okay, okay.
জি স্যার, থ্যাংক ইউ স্যার।
Okay, thank you,
আসসালামু আলাইকুম।
thank you. Allah Hafiz. Walaikum Assalam.
Assalamu alaikum, sir.
Walaikum Assalam.
আসসালামু আলাইকুম স্যার।
Walaikum Assalam.